Hello, everyone, and thank you for attending my master's degree defense, which is about analyzing the effectiveness of rainwater harvesting on runoff volume reduction in Harris County, Texas. I have edited and created some videos in the first few slides. I have made them help visualize the problems and what I want to discuss in this study. So I'm going to go through these while you are watching them. Rainwater from heaven. Sometimes we get too much, sometimes we don't get enough. We must have water to survive, to grow our food, to enjoy our homes, to run our industry, to improve our quality of life. In the water cycle, under natural conditions, rain or snow that precipitates onto the land, evaporates into the air, infiltrates into the ground, or soaks up by vegetation. The remaining of rainwater becomes runoff into the watershed and drains to the lowest point into the landscape, such as a river, local stream, lake, bayou, wetland, or stores as fresh water in lakes. Rapid urbanization has altered many natural water cycles, which have presented several challenges to local decision makers and created negative effects upon the local environment. Take a look out of your window when it's raining, even when it's not raining hard and it doesn't seem that significant. Some of the rain soaks into the ground, some gets taken up by plants, some gets cut in puddles, and some runs off downhill, usually into the street. One of the biggest challenges in the city is a proportions of all these different paths the water can take. All these streets, sidewalks, buildings, and parking lots cover the ground with impervious surfaces, which means that instead of water infiltrating, it runs off toward creeks and rivers, swelling them faster and higher and filling them with more pollution. Instead of acting like a sponge to absorb rainwater as it falls, urban watersheds act like funnels, gathering and concentrating rainwater runoff. Therefore, one of the biggest impacts on the environment of building anything is its effect on how water moves above and below the ground during storms. Here is some of the infrastructure that cities use to manage this massive challenge and few ideas in stormwater management that are slowly taking hold in urban areas. Increased runoff has been a problem since people started living in cities in the first place. And the first way we handled it was simply to get the water out and away as quickly as possible. That's because runoff creates flooding, and flooding causes billions of dollars of property damage and many lives each year. This solution is in the name that we still use for how cities manage storms: drainage. Most cities are organized, so the streets serve as the first path of flow for rainfall. Individual lots are graded with a slope toward the street, so that water flows away from buildings. The standard city street has a crown in the center with gutters on either side to water to flow. This keeps the road mainly dry and safe for vehicle travel while providing a channel to convey runoff. But the streets are not the end of the line. Eventually, the road will reach a natural low point and start back uphill, or will have collected too much runoff that it can't hold it all in gutter. At this point, the water needs a dedicated system to carry it away. In the past, it was common to simply put all the runoff from the streets directly into the sewage system. And actually, there is a really good reason not to do that. At the end of each sanitary sewer system is a wastewater treatment plant that was almost certainly not designed to process a massive influx of combined sewage and stormwater runoff. That's why most cities now use municipal separate storm sewer system, usually abbreviated as MS4. These are networks of ditches, curbs, gutters, sewer pipes, and outfalls only dedicated to moving runoff from everywhere in the city to the natural waterway. The stormwater management, through effective management of water resources, integrates the water cycle with the built environment through good planning and brings all of the elements of the water cycle together. Supply and demand, wastewater, rainfall and its runoff, as well as its contribution to local character, environment, and community. With this approach, we improve quality of life while addressing runoff pollution and water scarcity issues, changing water from potential nuisance into a valuable resource. In this way, with the pressing urban water demand, large funding needs, and potential of rising runoff, water conservation is a prevention method of stormwater management. Thus, collecting rainwater through installation of RWH system is a significant and effective solution to reduce water demand, cost, and maintenance on public water infrastructures. Rainwater harvesting is collecting rainwater and storing it for future use. It can be used for non-potable water such as landscaping, greenhouses, fire suppression, gardening, fountains, pools, livestock, and industry. RWH can be applied at every scale from our homes to large cities and towns. But how does it work? On a simple level, instead of letting rainwater from the roof run away down the stormwater drainage system, we could use it to water gardens, flush toilets, and laundry. In this way, we would relieve pressure on our water supply, reduce runoff from paved surfaces to minimize damage to valuable infrastructure and homes' water. A common question is how much rainwater we can collect if we are collecting rain off our roof. A 1-inch rain on 1,000 square feet roof will yield 624 gallons of water. In this study, Harris County, Texas is selected to assess the stormwater runoff reduction volume through retaining rainwater in RWH tank. Harris County is the third most populated county in the nation and is the most populous county in Texas. Our region is low-lying with flat topography, predominantly clay soil, and high average annual rainfall that contributes to frequent flooding. Harris County had the most total water use in Texas in 2018, and many of its underground water sources are being depleted. The Texas RWH Evaluation Committee has been established in 2005 to evaluate the potential of RWH and recommend minimum water quality guidelines and standards. It recommends the use of harvested rainwater for landscape watering and indoor non-potable uses such as machines and toilets. Furthermore, in Texas, tax exemption about purchasing RWH equipment and supplies is an incentive for installing the RWH system. Along with all RWH potential benefits as a LID technique, the hypothesis of this research is the installation of RWH tank on single-family houses in a neighborhood would reduce at least 30% volume of runoff flows to the stormwater drainage system. To deal with mentioned challenges and to help to achieve the goal of the stormwater management program, many studies have considered RWH as a LID to manage natural resources and contribute to sustainable urban development. Based on studies, stormwater management is the effort to reduce runoff of rainwater into streets and other sites to improve water quality. LID are systems that use natural processes to use of stormwater for protecting water quality. RWH is a retention to capture and manage stormwater at the source for water usage. And water sustainability in its three issues about demand, RWH can reduce 38 to 65% of water demand for toilet flushing and larger than 20% for irrigation. About economy, RWH can reduce utility bills and the impact on the stormwater infrastructure. About environmental issues, RWH can reduce the amount of polluted runoff and helping to bring flow and water quality back toward the pre-developed levels. How do we start? What are our requirements? How will the water be used? What products do we need? First question is always, what size tank do we need? Of course, the answer depends on what we will use the water for and in which study area. Gulfton, which is the most densely populated neighborhood in the city of Houston, is selected because it would be more efficient. Gulfton is in the Brays Bayou watershed, and the closest Harris County runoff gauge is located at Brays Bayou and Rice Avenue. The southeast corner of Gulfton is the most at risk for severe runoff. In this study, the census block group, which includes 227 single-family detached houses, those are located in the 100 or 500-year floodplain, is chosen to make it more manageable in scale and useful for future research. Here are dataset and variables those have been used in this study. The water catchment surface of the RWH system is the house rooftop. Water demand, which includes indoor and outdoor water usage, and asphalt composite roofing is common in Gulfton. It can leak chemical into the rainwater, so RWH system using this type of roof should not use the rainwater for drinking water. Therefore, in this study, toilet flushing and laundry were considered as indoor water demand. Precipitation is calculated using the daily rainfall data recorded in the gauge located near the southeast of Gulfton. Time frame used in this study is 10-year period, 2010 to 2019, to make results more understandable and better comparable. For tank size, the basic rule for sizing any RWH system is that the volume of water that can be captured or stored must be equal or exceed the volume of water demand. Total indoor water usage for a household with 3 people in single-family house for toilet flushing and laundry equals to 52.2 gallons a day. Outdoor water usage is about 80 gallons a day per house. Therefore, the tank with a capacity of 4,000 gallons would be adequate to capture the rainwater while assuming an empty tank first of each month. Daily water balance simulation for certain study area is executed without RWH tank and then recalculated with RWH tank for comparison. These calculations are performed at a daily rate for 10 years of precipitation recorded from 2010 to 2019, and total daily runoff amount without considering RWH tank is calculated based on equation 1. Daily Q is calculated by sum of multiplying the amount of daily rainfall by the size of different catchment areas and their specific runoff coefficients. For calculating amount of runoff with considering RWH tank, we need to determine amounts of rainwater can be stored in tank after end of each day. Equation 2 is used for this reason, which remains between 0 and tank size. It depends on total daily inflow to the rainwater harvesting tank of roof, water demand, and tank size. Daily inflow in the RWH tank of roof is determined based on equation 1 for roof to determine total daily amount of rainwater that can be collected from rooftop. Estimating daily runoff reduction volume with considering RWH tank requires calculating daily amount of rainfall retention, which is differences between the amount of rainwater that can be stored in tank after end of each day from rainwater stored in tank of the day before. To estimate percentage of yearly runoff reduction based on equation 3, daily amount of rainwater retention are added in each year and divided to the sum of daily runoff amount in the same day times 100. A total 160 simulations are performed and charts produced in the results section. As shown here, total daily water required for toilet flushing and laundry is about 33% of all daily indoor water demand. This amount plus outdoor water usage includes 55% of total daily water demand. Based on GIS street map and HAR, an average size of different catchment areas for a single family home in the study area are calculated. Total yearly rainfall for years from 2010 through 2019 based on the certain gauge in the study area were collected. The dry year is 2011 with 19 inches rain and wet year is 2017 with 81 inches rain. It is expected that years with more rainfall would have a higher chance of the tank remaining full and have less effectiveness on runoff reduction. During dry years, since tank is not being continually filled by rainwater, there would be more chance that tank becomes empty and effectiveness on runoff reduction increases. The annual reliability of the system to provide sufficient water to satisfy demand as a percentage is calculated. To evaluate this reliability, 160 simulations are performed by dividing sum of amount of rainwater that can be used for consumption on each day by total yearly amount of rainwater demand times 100. The results show that maximum achievable reliability is not observed for all considered scenarios. The reliability ranges between 43% and 73% for indoor water demand and between 24% and 65% for indoor and outdoor water demand. As charts show, the most reliable tank size is 3,000 gallons tank, which is shown in light blue. On average, a 1,500 gallon tank, which is shown in yellow, provides amount of rainwater same as other tanks with more capacity, except 3,000 gallons tank for both water demand scenarios. Overall, reliability of the system increases with more amount of yearly rainfall. Top figure shows total amount of yearly runoff without considering RWH tank in gallons, which is calculated from equation 1 and straightly depends on the amount of yearly rainfall in inches. Two other figures are from differences between equation 1 and 2. These figures are samples to show runoff volume with and without RWH tank in dry year and wet year. The maximum runoff reduction corresponding to the tank with the highest volume, which is 4,000 gallons. It's about 6.3 million gallons in dry year and 13.7 million gallons in wet year. Let's look at the table that I have prepared for this runoff reduction charts. As you see, although for each tank size, amount of runoff reduction increases with increasing water demand. But this increasing is not significant in dry year. And when size of the tank is more than 3,000 gallons, the increasing mode in runoff reduction is reversed to decreasing. Results of equation 3 show that for two different water demand scenarios, the percentage of runoff reduction ranges between 4% in wet year and 32% in dry year, depends on tank size. There is not a significant change of PRR for the same tank size with different water demand, which is between 0 to 3% increasing in PRR with more water demand. Overall, although PRR increases with increasing tank size, but in both water demand scenarios, PRR does not change significantly when tank size is more than 3,000 gallons. This study poses that the installation of RWH system by using rainwater reduces the impacts of runoff on built environment for all different scenarios. The most reliable tank size is a 3,000 gallon tank, which can supply up to 36% of indoor and outdoor water demand yearly. Also, installation of 3,000 gallon RWH tank in this study area with study assumptions has a critical potential to reduce runoff up to 30% with considering any of two water demand scenarios. Based on results on this study of 227 single-family houses in Gulfton with considering 3,000 gallon tank, an average diverting of stormwater is 9 million gallons yearly. This means that each house reduces about 40,000 gallons of stormwater runoff annually. Here, based on studies, installation of two 1,500 gallon tanks instead of one 3,000 gallon tank is recommended to have more chance for fitting in a lot area, and it has the advantage of emptying one tank for maintenance while other tank still has stored water. Results of this study supports the results achieved by many other studies about reducing demand of water from municipality, which can be by 14 to 36%. There are more than 380,000 single-family homes in Houston. If assumed that half of these homes use the municipal water supply, 7.6 billion gallons of rainwater yearly could be diverted from the stormwater system. This study results support other studies. Those concluded that heavy rainfall requires RWH tank with a higher capacity, and show that in this study, a 4,000 gallon tank has the most potential of reducing runoff volume annually. But in overall, in this study, the 3,000 gallon tank would be ideal size to reduce almost the same amount of runoff as the bigger tanks. Also, results support other studies about economy issues and shows that RWH system would be economically viable by saving money for water utility bills, with considering a sewer and stormwater runoff reduction at the city scale would be economically efficient. This study could be an alternative in future to the standard way of dealing with water supply and stormwater mitigation for developing municipalities. Based on the assumption that an owner empties the RWH tank every 2 weeks during each month, because in Houston, usually there is a short period between rain events that could cause overflow tank earlier, maybe it seems that this model could not be worked on other parts of the world with different rainwater patterns. But with using rainwater for more water usage or increasing density through applying RWH system in multi-story buildings, this assumption will happen automatically. Since this study area is located in the most densely populated neighborhood in Houston, the average catchment area values that were used in this model could be used as scale in the future or for other neighborhoods with equal or less density. Because in neighborhoods with less density, the percentage of impervious area is less than more dense areas, such as this study area. The amount of infiltered rainwater increases, and in turn, the volume of runoff is reduced. It is maybe argued about cost, how, and the possibility of installing separate plumbing in existing buildings to use collected rainwater through the RWH system for indoor water supply, which is for just toilet flushing and laundry. But given these results of this study, given the results of this study, that increasing the amount of water consumption has not a significant impact on runoff reduction. And also, as it seems, the plumbing in the exterior of building looks much easier. Can be concluded that even by installing the RWH system and using the saved rainwater only for outdoor water usage can achieve to the results similar to what was reached here. Also, maybe through some encouragements or regulations, the city can work on improving rooftop material for making the water collected from them be potable after some filtering process. Besides this, and as incentive for applying the used model in this study for anywhere with similar amount of rainfall characteristic with less rooftop area, it is recommended that the city offers installing extra shades regardless of its area in the building infrastructure. Moreover, for acquiring the best effectiveness, it is recommended to combine RWH system with other LID techniques such as infiltration trenches and bioretention cells. Here is the references of pictures and videos that I have used in my PowerPoint file. In the end, I want to thank dear Dr. Smith and dear committee members who helped me, guided me out in this project. Also, I appreciate my family, especially my amazing husband, supporting me, being by my side and pushing me to try harder. And finally, thanks to all of you for attending this meeting. Please let me know if you have any question regarding this research.
Thank you, Elahe. That was really good. So I would like to initially open up the questions to the committee. If you have any questions that you have for Elahe, and Ella, you may need to go back on some slides depending on the nature of the questions.
Okay.
So Dr. Chun, Ms. Escobar, Dr. Hwang.
All right, so I'm gonna go to the first. So presentation is so much better than your manuscript, so very easy to understand and very organized. So I love it. So I like to echo your research output. So basically, after installation of the water tank, we may need to think about the economic impact. So the reason why we do this kind of research activity is to for the kind of economic impacts damaged by hurricane or other natural disaster, right? So if there is no any benefit on the economic aspect, economic or impact, so we don't need to do that. So anyway, so have you ever think about how much this kind of system bring up positive impacts on the economic system? So for instance, recovery or maintenance, insurance, or human behavior, everything gonna be very impacted by the water tank. So I like to just know your idea what happened about that.
I have searched about that, about the economy issue, and they, as I mentioned in literature review, they mentioned that it's mostly for sewer and stormwater system. I've calculated about water utility. When you see that, you feel that it's not significant because every 1,000 gallon water costs you for $6 only. So when you see that, maybe first you think that it's not significant, but after that, when you add some issues about water supply infrastructures, a cost of what runoff happens for us, about losing lives or property damages, or what we need, what cost do we have about improving our stormwater drainage system. So most cities knows that when they improve or when they expand the stormwater drainage system, it will make the problem better. It may solve the problem, but in the experiences, they show that this kind of changing or improving stormwater management through extending the pipes or make them bigger, it's not work. And we have to do something like these LID systems and use the water in the source.
Okay, thank you.
So I'd like to also just congratulate you on the depth of the research, the literature review. I agree that your presentation makes it all come together in a nice, neat package, and I really appreciate that. So thank you for your hard work. I see the research you've done. I looked through all your literature review items, and I think you've did a great job of capturing this phase one. I think what Dr. Chun is saying is something that is of interest, but obviously this is focused on this part. But if you were to continue with other research or further studies, I think understanding that last recommendation you had in your results, which was combining systems, I think that's something that something that could be a worthwhile investigation to really figure out how could that have an impact on people's bottom lines of the homeowners. If there's a way for credits and for materials and supplies and installations to be provided to this community, and if it provides a tangible benefit to their bottom line operating expenses for every home, right? Like some way of doing relief in a community that could use it, right? But that also has an equal benefit that needs to be quantified for the municipalities. It all comes down to money. I think you've done a great job of getting right to that doorstep to say it's a valid point. It should be investigated further. So great job.
Thank you.
Mm-hmm.
Go ahead, Dr. Hwang.
Yeah, Alaya, you did a good job, and then yeah, it looks like you did a very hard work to prepare the presentation. Can you go to the title slide, the first slide of your presentation?
Title? Okay.
Yeah, title. Okay, so you said the runoff volume reduction. So you're focusing on the area-wide runoff volume reduction, or just a runoff volume reduction for like individual houses? Where do you focus?
Mm-hmm. I most focused on neighborhood area. In a block scale neighborhood, which has 227 single family detached houses. And as you know, about water usage, it restricts me because the information was for water usage was single family houses. So I've chosen those 227 single family houses. And then I've calculated all formula for those in Excel and the charts for all those 227 single family homes.
Okay, then in terms of flooding issues, how much of those rainwater harvesting systems can reduce a flood volume?
In that neighborhood that I have calculated with those assumptions that I have mentioned, I've reached that it can reduce up to 32% with 4,000 gallon tank and 30% with 3,000 gallon tank.
I mean, my question is like the flooding does not happen that every time that whenever we have rain. So flooding, I mean, happens that whenever the rain depth like above like a 1 inches, something like that. So if you select some like maybe 10 floodings we had maybe last year or last couple of years, then how much we can reduce the flooding using those runoff, I mean the rainwater harvesting system?
Mhm. Yeah, it's a good question actually, but you know that in my assumption, I use the daily data for each year and the results are yearly. So, and
So I mean, the reason I'm asking is like because you combined all the rain events all together, but small like a just light rains, they don't cause any flooding.
Mhm.
So let's say that if we have like maybe half inches of rain maybe every week, then it will not make any flooding in Houston area. The flooding mostly happen whenever we have maybe 2 inches of rain or something like that. So if you previously like search the data, when we had flooding in that neighborhood, then maybe if we had 10 flooding events like last year, then using the rainwater harvesting system, maybe we reduced maybe 2 floodings or something like that.
Yeah.
Then yeah, another question is, you assumed that the rainwater harvesting system, the water we collect using the rainwater harvesting system, that can reduce the consumption for the indoor and outdoor, but I think the people, they are highly reluctant to use gray water. So rainwater is gray water, not like a tap water. So they are highly reluctant to use gray water for indoor use. Like even for toilet, they really don't want to use any water for some like only few people they're willing to use gray water for some indoor use, but most maybe 99% of people they highly reluctant to use gray water for indoor use. So when you separate indoor and outdoor use, then maybe you can show the results. In the case when people only use the rainwater for outdoor use, and when people use the rainwater for both indoor and outdoor use.
Mhm. Okay. So about your first question about the flooding, yeah, it's a good idea to do another research for doing just the flooding events, because my study is most focused on runoff reduction. It's not on flooding, but it's.
I mean, runoff actually, the runoff is the cause of flooding. So.
Yeah. And actually, I think if you are not good with that, you can just feel that if this 30% or any percentage can extend the peak of runoff time.
Yeah, I agree. But because that 32% is just you combine the rain for whole year. So that's why I asked like yeah. I gave you the example. If we have like a 0.5 inches of rain like every week, we are not going to have any flooding. So that means you still can say, oh, the runoff, the rainwater harvesting systems can reduce 32% of runoff, but the runoff does not mean the linked to flooding every time. So flooding means like sometimes when we have maybe certain, I mean, I don't know what is like a cutoff between the like flooding or not, but runoff does not mean that it's flooding every time. So that's why I'm asking maybe someone else can figure out. I mean, maybe that's one of the reasons why the runoff harvest system is not that popular in Houston area, because if that is really critically beneficial, then I believe that in my community, I haven't seen any single like barrels of rain harvesting, rainwater collections system. So maybe that's why maybe you better like separate or making different assumptions. So the two give you the like a real impacts. Maybe you can pick the certain storms which we had flooding.
Mhm.
And then in those cases, like whether those rainwater harvesting systems could it reduce maybe even like a 5% of reduction could be critical in certain flooding cases. So
Mhm.
instead of it can reduce 32%, that's you just simply combine the whole year.
Yes, yes, it's a
So
good.
maybe in your conclusion, maybe you can say, for example, in 2020, we had the 10 floodings. Using those rainwater harvesting systems, maybe we were able to reduce the flooding from 10 to maybe 7 or 8, something like that.
Mhm.
So then this is also linked to Dr. Chun's questions, how it will be linked to those economic impacts.
Yeah. Yes, it's a great point that you mentioned. Thank you.
Oh, okay, yeah, that's all.
So I want, oh, sorry, go ahead, Dr. Smith.
No, I'm gonna tandem, so go ahead if you want to.
Oh, well, I was going to mention I'm hearing the questions, and I think it's important to note that, like with my background in engineering, to answer those questions, the process that's necessary is typically a 2D engineering model, so that you can actually quantify the volume once you actually have your system plugged up and water's backed up to the street level. It's very highly dependent on the infrastructure below the ground as to when your flooding will happen. Some people have flooding and they actually have infrastructure that's properly sized, but the placement, the clogging, the maintenance has different issues, right? Flow lines and whether water can reach all the various drainage systems changes when something floods. And I think that to answer that question genuinely, you'd have to really go into an engineering exercise, which seems like it'd be a little bit beyond the scope of what this intention is, but it'd be a brilliant next thing for someone to do or for you to collaborate in doing. But that I understand that may not be 100% accessible to you to do, because I've had to do that before, and it's taken me a year of 2D modeling to quantify 3 or 4 streets throughout Houston, and I had to map out all of the topography and all of the infrastructure to capture it, and it's never what you expect in Houston with Houston's history and infrastructure. So I applaud what you've done, and I think these next steps and these next questions are great next questions. I think that having that next question answered is actually more of the reason why we don't have the adoption, and then the regulations that support it are the other part. But I know those are actually changing as well, and I know the people who are working on those things, low impact development and underground storage and rainwater harvesting. And so it's just, I think it takes another level of effort and research and professional practice to get to implementing those solutions. But they are being done here in Houston. I know dozens of people who do them, but it takes so much effort and so customized that I just wanted to make sure I offer that to temper that expectation.
Thank you,
Was
Son.
that-
I want to jump in on 2 things. When LA first started, it was about flood reduction. And so we initially had that conversation and realized it was a much bigger endeavor, and really just kind of what Zion has just said. And that's why we kind of backed into volume reduction, especially as we think about, plan a thesis and working within the skill set of not just her faculty, but just recognizing the direction and whether or not is it flood reduction or is it runoff, which we know can lead to other issues. And so just kind of echoing that. And the one thing I will say, Dr. Hwang, is as LA has started this, I decided I would try catching my own stormwater. And I agree with you. I am one of those individuals who does not like to use gray water, but under Storm Uri, I actually used my gray water for my toilet because the water everything was happening, and I had these buckets. It wasn't a sophisticated system, but I had these buckets of water, and I was so grateful that I did. And I'm going to need a new roof, but I've already worked through it won't be 3,000 gallon tank, mind you, It'll be something nice and cute that I get from Home Depot. However, I am using it I built a garden, so I am having outdoor use, and for emergency purposes, I do have it. And so I do agree with Dr. Hwang, what he said, that most people are hesitant, but if you hit an emergency situation, having that, and given in Houston, we have 1 or 2 emergency situations a year. I think that the mindset may change. And so Ella, hey, I definitely would add that to your conclusions, your recommendations, and I think you hinted on it, that people may not really be ready for indoor. And so I think you did provide just the outdoor. But the one question, I have a question. In your results, you mentioned the billions of water that is saved. Is that on the heaviest rain day, or you're averaging the heaviest rain days with the lightest? Because you make some assumptions about how much water can be diverted. Is that based on the heaviest rain year, the lowest rain year, or a combination of both?
I've done between 2010 through 2019, and this is the average between dry year, which is 2011, and wet year, which is 2017.
Okay, the average. Okay, all right, thank you. Dr. Chun, you had a?
Yeah, I just curious, quick question. So, Dr. Smith, you use the gray water indoor. So, is there any water filter to use the kind of the collected gray water?
No, just right off my roof.
Oh, okay, yeah.
But I recognize I needed to. But when the water went out, I couldn't flush. I remembered I had those gallons of water.
So maybe there is some kind of the filtering system that we can avoid using the gray water.
You can use a cheesecloth. In the short term, down and dirty, you can use cheesecloth. That will get out of any of your particles if you're in an emergency situation on the top.
Yeah.
I did use a strainer. I could say I did use a strainer. But
there actually are carbon filters that, the way this is done, I've actually been part of installing these in Peru. And essentially you connect that downspout to a tank, and when it comes out of the tank, it actually goes through 2 carbon filters that you have to change out depending on your water use. And then what comes out of that is filtered in the way you would have like a Brita pitcher filter. So it's a polisher. It's not reverse osmosis system, but you can attach that. Those are about $900. And you can store them in the garage.
How much?
About 900 sometimes.
No, the cheesecloth really works.
No, I mean, if you really want to go to that other extent, but I agree. And if I'm not mistaken, I think your research said that you were sticking only to outdoor usage, and the results and the numbers you were sharing with us was only for outdoor. You had excluded indoor from this exercise after you determined that indoor was going to be, there was going to be hesitancy and it's a little bit more complicated, but you could do outdoor non-potable uses only, which was right. Right. Although I did see clothes washing in there, so that's indoor. Yeah. But there's ways to get it done. I think honestly the difficulty is there's process, there's plumbing, there's design, there's customization, and you're not going to find hundreds of thousands of homeowners who are going to take that on themselves. They're going to need guidance. They're going to need a team of people. They're going to need professionals who offer this service. And that's what's missing in the market, is more professionals that have this as a specialized skill. I've worked with those professionals, and there are very few of them. And that's really the hurdle. There are very few people who can offer this to you as a turnkey service and say, it's $5,000, I'll do it for you, and you're done. If that was available, that would change the market, I think, dramatically.
Okay. Thank you, Zion. Do we have any questions from our guests in the audience? Brother, husband, father, any of you have any questions from the presentation?
I think they don't. Okay.
I am the husband, and I've had my questions. I mentioned it to her, so all those maybe included or answered. but I've seen her that she worked very hard, and I'm very proud of her, and I congratulate her. Thank you, everybody.
Thank you for joining us.